Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is Norton's Theorem applied to DC circuits. Our objective today is to learn to employ Norton's Theorem in an effort to simplify a complicated linear two-terminal network into its Norton's equivalent circuit. Ideally, the original and the Norton's equivalent circuit will behave identical to each other. However, the Norton's equivalent circuit will be notably easier to build and solve for desired electrical quantities. Bottom line up front. Norton's theorem is Thevenin's theorem with two subtle twists. Norton's theorem, like Thevenin's theorem, has the power to render even the most tangled and gnarly of circuits into tame and docile simplified circuits that sit, stay, and roll over on command. The first difference being that the Thevenin's theorem uses an equivalent voltage source, whereas Norton's theorem uses an equivalent current source. The second difference being that Thevenin's theorem is a series arrangement of resistances, whereas Norton's theorem uses a parallel arrangement of resistances. It's really that simple. If your sponge is full and you simply cannot cram another theorem into your head at risk of forgetting something else, you can think of Norton's theorem as Thevenin's theorem with a source conversion, and that is totally cool by me. This does, however, imply that one is well versed in Thevenin's theorem and source conversions. If you haven't watched the Thevenin's theorem or the source conversion lectures yet, both available at the Big Bad Tech channel, please do so now, since we'll be regularly making use of both of them during the course of this lecture. Other methods of arriving at the Norton's equivalent circuit exist, and importantly, all these methods should yield the same result. In addition to indirectly arriving at the Norton's equivalent circuit using a Thevenin's theorem and source conversion, we'll discuss the direct and experimental observation method. Norton's theorem, like Thevenin's theorem, is used in scenarios involving the response of a variable load resistor to a complicated circuit. Every time the variable load resistor changes value, it necessitates a completely new series parallel circuit analysis. This is a serious drag. The better way is with Thevenin's theorem. Norton's theorem does yield an equally easy circuit. However, it is not my preferred technique, because you're not often given access to a current source in a basic lab setting. This being said, the Norton's equivalent circuit does simplify circuit analysis. Norton's theorem simplifies a complicated circuit into a single current source, called the Norton equivalent current source, IN, in parallel with a single resistance, called the Norton equivalent resistance, RN. The original complicated circuit and the Norton's equivalent circuit should ideally behave the same, and importantly, the load resistor should be none the wiser to the substitution. Of note is not only the substantial ease with which calculations can be made using the Norton equivalent circuit. After all, it's just a pure parallel circuit, but also how much less components, connections, and confusion is involved in the physical construction of the Norton equivalent circuit. Which would you rather be responsible for? A complicated series parallel circuit or a simple pure parallel circuit with only two elements? I know which one I'd prefer. Let's dive right into Norton's theorem using the indirect method. This method has us solve for the Thevenin's equivalent circuit and then perform a source conversion. By all means, pause the lecture and determine the Thevenin's equivalent circuit seen by the load resistor RL. Don't do the source conversion just yet, because I want to make use of Thevenin's equivalent circuit to prove a point. If you applied Thevenin's theory correctly, you should have obtained the following equivalency. This complicated series parallel circuit supplying variable load resistor RL can be simplified into a pure series circuit consisting of the Thevenin's equivalent voltage ETH at approximately 9.8 volts and the Thevenin's equivalent resistance RTH at approximately 166.2 ohms. Let's say RL takes the following three values: 80 ohms, 160 ohms, and 320 ohms. Pause the lecture and calculate both the voltage across and the current through the variable load resistor RL at these three settings, using your choice, either the original complicated series parallel circuit or the simple series Thevenin's equivalent circuit. Have I made my point? The Thevenin's equivalent circuit is much easier to solve for the desired quantities than the original complicated series parallel circuit when presented with a range of load resistance values. It does take some upfront labor, but yields a notably easier circuit when presented with repetitive scenarios. If you did everything correctly, you should have found the following voltage and current values experienced by the variable load resistor. Note that using the Thevenin's equivalent circuit, you most likely use the VDR to solve for voltage across the variable load resistor first, and then used Ohm's law to solve for the current through it. Now, pause the lecture and use source conversion to change this voltage source in series with a resistance to a current source in parallel with a resistance. If you did the source conversion correctly, you should have found that the magnitude of the current source is approximately 58.8 milliamperes, and that the parallel resistance is 166.2 ohms. Note the resistance is the same magnitude, only its orientation has changed. Ta-da! You just found the Norton's equivalent of this original circuit, and we're only a little way into this lecture. That's the point. Make use of the skills you already have to shortcut to the results you seek. Let's again say that our variable load resistor takes the following three values: 80 ohms, 160 ohms, and 320 ohms. Pause the lecture and calculate both the voltage across and the current through the variable load resistor RL at these three settings, using your choice, either the original complicated series parallel circuit or our new Norton's equivalent circuit. This is again the point of establishing an equivalency. The Norton's equivalent circuit is much easier to solve for the desired quantities than the original complicated series parallel circuit when presented with a range of load resistance values. If you did everything correctly, you should have found the following current and voltage values experienced by the variable load resistor. Note that using the Norton's equivalent circuit, you most likely use the current divider rule to solve for the current through the variable load resistor first, and then used Ohm's law to solve for the voltage across it. It really is a matter of personal preference. Some people like using the Thevenin's equivalent circuit and the VDR. Some people like using the Norton's equivalent circuit and the CDR. I'm a Thevenin's and VDR man myself for this compelling reason. Walk into a basic electronics lab and go get me a current source. Ordinarily, not going to happen. Most basic electronics labs do, however, have access to voltage sources. Additionally, I like the VDR because it's a directly proportionate ratio, whereas the CDR is one of those annoying indirectly proportionate ratios that takes a moment of consideration before application. Regardless, the results experienced by the variable load resistor are the same for all three circuits: the complicated original series parallel circuit, the Thevenin's equivalent circuit, and the new Norton's equivalent circuit. That's the point. All three circuits are equivalent, and the variable load resistor RL should be none the wiser to the substitution. You, however, will be. The Thevenin's and Norton's equivalent circuit are substantially easier to solve for the desired quantities. Direct means of determining the Norton's equivalent circuit exist that bypass the Thevenin's equivalent and source conversion detour. This is a two-step technique, one step of which is identical to that used in Thevenin's theorem. To simplify a complicated circuit into its Norton's equivalency, we need to solve for the quantities IN, the Norton's equivalent current source, and Rn, the Norton's equivalent resistance. Let's start by discussing the procedure necessary to solve for IN, the Norton's equivalent current source. First, one must remove the load resistor from the nodes of interest. Next, one determines the short circuit current seen by an ammeter placed in the former location of the load resistor. In this example, we've designated resistor RL as our resistor of interest. As previously discussed, any change in RL would necessitate a complete series parallel circuit analysis to solve for the circuit's response to the changed resistance. Let's determine the Norton equivalent current seen by the load resistor attached to this circuit. Step 1. Remove the load resistor from the nodes of interest. Step 2. Determine the short circuit current seen by an ammeter in this location. An ammeter in this location would short out the 220 ohm resistor, and the only thing limiting the 40 volt source is the 680 ohm resistor. Short circuit current is therefore 40 volts over 680 ohms, or 58.8 milliamperes, exactly what we obtained during our previous indirect source conversion method. Now that we've obtained the Norton equivalent current source, IN, let's set it aside and move on to Rn, the Norton's equivalent resistance. Similar to the warning I issued in the Thevenin's theorem lecture, Rn and In have nothing to do with each other until the very last step. Set In down and do not pick it up again until we're done. To solve for Rn, use the exact same techniques one utilizes to solve for RTH, the Thevenin equivalent resistance. This necessitates a multi-step process. First, one must remove the load resistor from the nodes of interest. Next, one removes the source or sources from consideration. One removes a voltage source by replacing it with a short. One removes a current source by replacing it with an open. Make note that incorporating shorts and opens inside your original circuit may fundamentally change the nature of your circuit, as we'll see in a moment. Finally, one reads the resistance of the modified circuit at the terminals of interest. This is, in my experience, one of the hardest shifts for individuals to make. Rn is not the resistance seen by the original source. Rn is the resistance seen at the terminals of interest when the source has been removed. Again, make note that shifting perspective within your original circuit may fundamentally change the nature of the circuit, as we'll see in a moment. In this example, we've designated RL as our load resistor. As discussed previously, any change in RL would necessitate a complete series parallel circuit analysis to solve for desired quantities. Let's determine the Norton's equivalent resistance seen by this load resistor. Step 1, remove the load resistor from the nodes of interest. Step 2, remove the source or sources from consideration. In this case, it's a single voltage source, necessitating it to be replaced with a short or 0 ohm resistor. Finally, one reads the resistance of this modified circuit at the terminals of interest. If you want, you can draw a little ohm meter on the terminals of interest, reminding you perspective has shifted. The removal of the source and perspective shift changes the game, and a lot of people unnecessarily freak out about this. Chill out, relax. Visualize this circuit at the nodal level and from the perspective of flowing current. In this circuit, an ohm meter reading resistance from A to B would see the 220 and 680 ohm resistor in parallel with each other, for a total resistance of 166.2 ohms. This is fundamentally different than the relationship we previously observed when calculating the short circuit current IN. That's the point. There has been a perspective shift, and calculating RN has nothing to do with IN. Now that we've obtained the Norton's equivalent resistance RN, let's set it aside and take a break to discuss what just happened. Again, solving for Rn and In had nothing to do with each other. There's an impenetrable brick wall between them, and they can be solved for in the order of your choosing. In and Rn only come together in the final step. Of note, we obtain the same simplified representation as we did earlier using our indirect Thevenin's equivalent and source conversion detour. Like I said earlier, if your sponge is full and you simply cannot cram another theorem into your head at risk of forgetting something else, you can think of Norton's theorem as Thevenin's theorem with a source conversion, and that's cool by me. The results are the same. If, however, you want a simple and direct method of calculating the Norton equivalent circuit, that option is also available. With consideration of ethical work practices, I want you to obtain correct results by any means necessary. A third method of obtaining the Norton's equivalent current and resistance values exist. On a practical level, if one was to really build the original circuit, one could experimentally determine the Norton's equivalent resistance using identical techniques. First, you would remove the load resistor from the node of interest. Next, one would remove the source or sources from consideration. One removes a voltage source by replacing it with a short. Note, do not short out the voltage source. This is a surefire way to get stuck in the iron chair position for the rest of your academic career. Remove the voltage source first. Replace the terminals formerly occupied by the voltage source with a short or 0 ohm resistor. Finally, one would read the resistance of this modified circuit at the terminals of interest. An ohm meter in this position would again see the 220 ohm resistor in parallel with the 680 ohm resistor for a total resistance value of approximately 166.2 ohms. To experimentally determine the Norton's equivalent current, one would remove the load resistor from the nodes of interest and insert an ammeter. An ammeter in this position would again short out the 220 ohm resistor and read approximately 58.8 milliamperes of current. Whether you indirectly or directly calculate or experimentally observe the Norton's equivalent current and resistance, the results are the same, and they are notably much easier to conceptualize and utilize than our previous complicated series parallel circuit. The Norton's equivalent circuit will behave exactly the same as the original circuit, and the variable load resistor will be none the wiser to the substitution. One learns Norton's theorem by doing Norton's theorem. Let's try another illustrated example. By all means, pause the lecture and attempt to solve for the Norton's equivalent of this linear two-terminal circuit supplying variable load resistor RL. Use whatever method floats your boat, the indirect Thevenin's equivalent source conversion method or the direct two-step method. Those that use the indirect Thevenin's equivalent and source conversion method would have obtained the following intermediary Thevenin's equivalent circuit. Again, this lecture operates under the presumption you are skilled in Thevenin's theorem. If you need help with Thevenin's theorem, by all means watch the Thevenin's theorem lecture available at the Big Bad Tech channel. A Thevenin's equivalent circuit is an approximately 47.7 volt source in series with an approximately 5,767.9 ohm resistor. The source conversion of this Thevenin's equivalent to the Norton's equivalent yields the following simplified representation: an 8.3 milliamp current source in parallel with a 5,767.9 ohm resistor. This is the Norton's equivalent circuit. One can also directly calculate the Norton's equivalent values. To directly simplify a complicated circuit into its Norton's equivalent circuit, we need to solve for the quantities In and Rn using two separate steps. Here's how I applied the direct calculation method. To solve for In, the Norton's equivalent current, first one must remove the load resistor from the nodes of interest. Next, one determines the short circuit current seen by an ammeter at the location formerly occupied by the load resistor. With the ammeter in this position, current will flow in the following fashion. We need to solve for the current through the 3.9 kilo ohm resistor. The 3.1 kilo ohm and the 3.9 kilo ohm resistor can be taken in parallel, a simplification I'll call R single prime, where R single prime has a value of approximately 1.727 kilo ohms. The source in this case would see a total resistance of approximately 6.427 kilo ohms. Source current would be source voltage divided by total resistance, or approximately 18.7 milliamperes. If 18.7 milliamperes enters the parallel combination formed by the 3.9 kilo ohm resistor and the 3.1 kilo ohm resistor, we can use the current divider rule to solve for current experienced by the ammeter. The CDR set up to solve for the current experienced by the ammeter is as follows, which again yields 8.3 milliamperes. To directly solve for Rn also necessitates a multi-step process. First, one must remove the load resistor from the nodes of interest. Next, one removes the source or sources from consideration. One removes a voltage source by replacing it with a short. One removes a current source by replacing it with an open. Make note that incorporating shorts or opens inside the original circuit may fundamentally change the nature of the circuit. Finally, one reads the resistance of the modified circuit at the terminals of interest. In this case, the ohm meter would see the 3.1 kilo ohm resistor in parallel with the 4.7 kilo ohm resistor, and this parallel combination will be in series with the 3.9 kilo ohm resistor, for a total resistance of approximately 5,767.9 ohms. Using either method, the Norton's equivalent circuit for this original circuit is the parallel combination of In, an 8.3 milliampere current source, and Rn, an approximately 5,767.9 ohm resistor, supplying a variable load resistor RL attached to the nodes of interest. If everything I've been telling you is true, the Norton's equivalent circuit should behave exactly the same as the original circuit, and the variable load resistor should be none the wiser to the substitution. Let's see if this is the case. Pause the lecture and solve for voltage across the variable load resistor and current through the variable load resistor when RL is 2.5 kilo ohms, 5 kilo ohms, and 10 kilo ohms using the original circuit, the Thevenin's equivalent circuit, and the Norton's equivalent circuit. Using either circuit configuration, you should have obtained the following values. Of note, the Thevenin's equivalent and Norton's equivalent circuits are much simpler, being either pure series or pure parallel circuits. If we needed to perform the same analysis for a larger range of RL values, the Thevenin's or Norton's equivalent circuits would yield the same results, only faster. Let's close out this lecture with another illustrated example. By all means, pause the lecture and attempt to solve for the Norton's equivalent of this linear two-terminal circuit supplying variable load resistor RL. Use whatever method floats your boat. the indirect Thevenin's equivalent and source conversion method, or the direct two-step method. Be warned, this one's a little tricky. It's going to require the superposition theorem and attention to detail. Note the polarity of the voltage and current source. Those that use the indirect Thevenin's equivalent and source conversion method would have obtained the following intermediary Thevenin's equivalent circuit. Again, this lecture operates under the presumption you are skilled in Thevenin's theorem, and in this case, superposition theorem as well. If you need help with Thevenin's theorem and superposition theorem, by all means revisit these lectures available at the Big Bad Tech channel. The source conversion of this Thevenin's equivalent to the Norton's equivalent yields the following simplified representation, where IN is found to be 150 milliamperes and RN is found to be 142.9 ohms. Again, note the polarity of the resultant current source. One can also directly calculate IN and RN. Since we're crazy, let's solve for RN first. To solve for RN necessitates a multi-step process. First, one must remove the load resistor. Next, one removes the source or sources from consideration. One removes a voltage source by replacing it with a short. One removes a current source by replacing it with an open. Make note that incorporating shorts and opens inside this circuit may fundamentally change the nature of this circuit. Finally, one reads the resistance of this modified circuit at the terminals of interest. In this case, the ohm meter is reading the 200 and 500 ohm resistor in parallel with each other, such that Rn, the Norton equivalent resistance, is equal to approximately 142.9 ohms. To solve for IN, the Norton's equivalent current, requires two separate analyses if we are to use superposition theorem. Let's perform our first analysis from the perspective of the voltage source. In this case, we need to remove the current source by replacing it with an open. To solve for the Norton's equivalent current, first one must remove the load resistor from the nodes of interest. Next, one determines the short circuit current seen by an ammeter at the location formerly occupied by the load resistor. With the ammeter in the current location, no current will flow through the 500 ohm resistor because it is shorted out. In this case, the 200 ohm resistor is the only opposition to current flow. From the perspective of the 40 volt source, this ammeter will experience 40 volts divided by 200 ohms, or 200 milliamperes of current. Importantly, current from the perspective of the 40 volt source is going down, flowing from A to B. This all changes when we look at Norton equivalent current from the perspective of the current source. We need to remove our voltage source by replacing it with a short circuit. To solve for the Norton equivalent current induced by the current source, one must remove the load resistor from the nodes of interest. Next, one determines the short circuit current seen by an ammeter at the location formerly occupied by the load resistor. Note that I have defined my ammeter location as A being the indoor and B being the outdoor. From the perspective of the 50 milliampere current source, this short circuit has fundamentally changed the behavior of our circuit and has effectively shorted out both the 200 and 500 ohm resistor, meaning all 50 milliamperes will travel through the ammeter in an upwards direction from B to A. The ammeter accounting for polarity would therefore read negative 50 milliamperes. This may require some visualization and thought to see this effect. Notice when the two effects are superimposed upon each other, where 200 milliamperes goes A to B and 50 milliamperes goes B to A, we are again left with 150 milliamperes going from A to B. Either method yields the Norton equivalent circuit for the original circuit as the parallel combination of IN, a 150 milliampere current source pointed upwards, in parallel with RN, an approximately 142.9 ohm resistor, supplying a variable load resistor RL attached to the nodes of interest. If everything I've been telling you is true, the Norton equivalent circuit should behave exactly the same as the original circuit, and the variable load resistor should be none the wiser to the substitution. Let's see if this is the case. Pause the lecture and solve for voltage across the variable load resistor and current through the variable load resistor when RL is 70 ohms, 140 ohms, and 280 ohms using your choice, the original circuit or the Norton's equivalent circuit. Using either circuit configuration, you would have found the following values. Of note, both the Thevenin's and Norton's equivalent circuit would be much simpler, being either pure series or pure parallel circuits. If we needed to perform the same analysis for a range of R values, the Thevenin's or Norton's equivalent circuits would yield results faster, especially considering this is a multi-source network requiring a two-step superposition theorem for each change in RL value. Of note, consider the power dissipated by the load resistor at these three different RL values. Note when RL is close to either the Thevenin's equivalent or Norton's equivalent resistance, power dissipated by the load resistor is greater than resistors on either side. We'll learn in later lectures that maximum power is dissipated by the load resistor when the load resistor is equal to the Thevenin's or Norton's equivalent resistance. That's it. Let's bring this lecture to a close. Again, I'm a results-oriented person, and I'm urging those of you struggling with directly calculating the Norton's equivalent circuit to simply stop struggling and use a different method. You simply must know Thevenin's theorem for later progress in the basic electronics series. Direct applications of Norton's theorem is nice to know. However, if you're well versed in Thevenin's theorem and source conversion, you've already got Norton's theorem in your quiver. Like I said previously, they're rooted in math and hard science. Circuit analysis can also be thought of as an art form, which the finer points simply cannot be taught, but only learned by an individual. By all means, develop your own style of circuit analysis. Use techniques you like. Don't use the ones you don't. Use techniques you're good at and practice the ones you're not good at. The point is, there are many methods of obtaining the correct result, but ultimately, there is but one correct result. Later theorems like the maximum power transfer theorem are predicated upon your understanding of Thevenin's theorem and to a lesser degree, Norton's theorem. I'm encouraging you to get some practice with these techniques and seek help if you're struggling. Again, the only way to learn Thevenin's theorem and Norton's theorem is by doing Thevenin's theorem and Norton's theorem. Practice. In conclusion, we learn to employ Norton's theorem in an effort to simplify a complicated linear two-terminal network. Ideally, the original and the Norton's equivalent circuit will behave identical to each other. However, the Norton's equivalent circuit will be notably easier to build and solve for desired electrical quantities. Remember to view these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.